I welcome you all to the Impact Scholar Seminar, and this presentation is going to be done by all the students who have been working for last 6 months for our Impact Scholar program. It is an extension of the Neuromath summer courses, and they have been working in an international team with mentors from eminent universities around the world. And we have the BERTies and Oncodam today, mentored by Joseph de Molina and Andrew Jayabos Sundar, respectively. And then we will have Tiny Rodden Decision, that's a computational neuroscience team, mentored by Mayankar Mehta. And we are really happy and excited to know what you have been doing and how your overall experience was. And after each of the presentation, we will have like a short question answer round, and each of the group will get like 20 minutes to present. So with all this, I once again welcome you all, and we all appreciate all the effort you have been putting in this presentation and in this research work. So let's start with the BERTies.
Thank you very much for this introduction. We are presenting in the ISB seminar on enhancing human empathy in conversations using transformer-based models. Our group, the BERTies, consists of PARTHA, Cherishma, Endriyas, and Zahra. Our mentor, Joseph, has been invaluable in guiding us. The next slide, please. To begin with, we need to understand the importance of emotion recognition in large language models. Large language models are expected to become more empathic and capable of recognizing emotions when communicating with humans. As highlighted here, emotion recognition involves identifying and analyzing emotions from various inputs, such as text, visuals, or speech, to better understand human emotional states. We aim to leverage the capabilities of transformers to accurately identify emotions in multi-turn text dialogues. This forms the backbone of our research. And in the next slide, here we delve into the key findings from our literature review. To enable machines to recognize, understand, and respond with greater empathy and sensitivity within dialogues, they should be able to classify emotions. Our primary objective is to evaluate transformer-based models to enhance human empathy in dialogues. Techniques such as context-aware learning, instruction tuning, and emotional chain of thought methods are particularly promising. However, several challenges persist, including the limitations of one-hot encoding for overlapping emotions and the difficulty of addressing subtle and mixed emotions. This brings us to the critical research gap. Human attributes like empathy, linguistic creativity, situational awareness are ignored by AI systems in multi-turn dialogues. So we focus on this subject. Now I ask my friend Partha to continue with the next slides.
Thank you very much, Zahra. So very interesting introductions, and I acknowledge the importance of this data set to identify how human emotions are being recognized by various modern large language models and recent AI systems. We started looking into different available data sets. Finally, we decided to work on daily dialogue data set. which is a very popular multi-turn conversational dialogues being prepared by different annotators. So when these annotators started preparing these datasets, they mainly focused on these 7 emotion classes named as neutral or no emotion, anger, disgust, fear, happiness, sadness, and surprise. The top right of this slide, we'll see the distribution of each of these emotion classes in the entire dataset. Apart from that, there are various dialogue acts which helps us to enhance the understanding of background of those conversations and the narratives that are available within the datasets. Those dialogue acts are inform, question, directive, and commissive. These 4 different types. But even though these annotators prepared this dialogue, daily dialogue, which is a pretty well-known research paper, these datasets are not directly available to work at the first instance. So we have to pre-process a lot of things. We see that there is an emotion distribution on the middle right, that few classes has availability of huge number of times, more than 80 percentage, with occurrence to the all other remaining classes. So in this case, the pre-processing is necessary so that the model is not biased toward one particular classes, and it will treat all other remaining classes equally. For those, we followed basic NLP pipeline pre-processing techniques. For example, removing of duplicates or duplicated sentences, words, removing punctuations, symbols, spaces, extra characters, applying these regular expressions filters, removing outliers, and using of NLTK library to remove the stop words. And we know that these stop words are high frequent but less important words. So removing the stop words will give the model to focus on important words available within the sentence. Thereafter, the second part of the pre-processing is to apply sampling, because there are some classes has a lot of presence and some classes has almost no presence of all. So we have to normalize. And to have this normalization, we applied random sampling to mitigate this class imbalance problem and to reduce the dominance of this zeroth class, which is neutral class, and to upsample all other remaining classes. Moving on, once this data processing is completed, we started moving towards the training of our model. So we worked on pre-trained transformer model, BERT, and 2 of its variants, Distelbert and Roberta. Following are these hyperparameters, which we experimented throughout our experimental process. Loss function we decided with categorical cross entropy because it is multi-classes. And optimizer, we worked on Adam and Adam W, but these bold outs are which we finally decided to stick on. And Adam W works better with the learning rate 2 into 10 to the power minus 5. We also tried with 0.001 as learning rate. Batch size we tried with 32, 64, 128. However, 64 gave us a better results, and epoch with 30, 50, and 60. Again, 50 give us a better results with corresponding weight decay 0.1 and 0.001. With this experimental setup, this is another interesting slide. So results. On this slide, the rows are the models, and each of these models we worked on 50 iterations. Columns are the evaluation metrics. Accuracy with percentage, F1 score with percentage, number of tensors being saved in each of these deep neural network. We know that in neural network, first we'll go with the forward propagation, and then we came back with the backward propagation to um, fix up and to optimize the weights to get a better results. So the models for each of these models, 2 variants, cased and uncased. So for Distelbert, cased and uncased, followed by Roberta base cased and uncased. Thereafter, Llama 3.21 billion parameters model, BERT base case and uncased, and BERT large case and uncased. Among all of these, we saw that Roberta base uncased worked out the best, with the accuracy correspondingly 68.5% and its F1 score 75.4, which is pretty much higher with all other uh, existing models results. And we saw during the forward propagation 191 matrices. We know that In PyTorch implementation, tensors are n-dimensional matrices. So 191 matrices being saved, and in backward propagation, total 30 matrices are saved, and this gives us the advantage of not being recomputed during the gradient calculation. So the time got saved. Once the experiments with all of these models gets over, we saw how well we are with our experiments and what are the importance of these results. We see that existing baselines with all of these remaining works are pretty lower than with our current work, which is Roberta. For this model, Roberta based uncased with 75.4% F1 score, which is pretty higher than the existing baselines. And that gives us that whatever we decided with this experimental setup works better for this particular daily dialog dataset for this model. Moving on, so now I'll hand over to Cherishma for the final conclusion and the limitation with future directions.
Slide. Thank you, Partha. So to summarize what I said, our study demonstrates that the Roberta-based uncased model significantly outperforms other models, including Hilbert and its variants. So there's an accuracy of 68.5% and an F1 score of 75.45%. And this highlights Roberta's robustness in handling the data set that we used. But for the limitations, we identified a key limitation as the random sampling may lead to model overfitting, while using class-wise data point normalization tends to reduce the accuracy. So addressing this challenge required balancing between data representation and model generalization. So coming to the future direction, we plan to forward this to other data sets such as IEMO-CAP and in order to enhance the model performance. Additionally, we aim to extend our work to mental health and other high-stake sensitive domains by incorporating multi-model data, thus making the model more versatile and applicable in real-world scenarios. Next slide. Next slide.
Thank you very much. So if there are any questions, we can definitely take them.
Thank you.